Are you ready for a beast of a problem? Well, put your thinking caps on. Here we go. This is Hardy-Weinberg chi-square. So this video, I'm assuming that you are pretty solid on Hardy-Weinberg to begin with, not that you're learning it for the first time, because we're gonna just jump right into components of Hardy-Weinberg that you should know: P, Q, P squared, Q squared, 2PQ. We are going to use Hardy-Weinberg chi-square to determine if a population is evolving. Hardy-Weinberg is basically a null hypothesis. If those 5 conditions are met, then a population would not be evolving. But as we've talked about, those 5 conditions are always violated, right? So populations are basically evolving. But we can use chi-square to numerically, quote unquote, prove that a population is evolving or not. Here we go. Your basic steps. We're going to set up an observed versus expected chart. We have to work with alleles, use our frequencies to determine expected genotypes, use that to figure out individuals, and then run chi-square. There are a ton of steps to this set of problems. You're going to need a lot of paper. Here's our problem. So I found this problem online. It's a really great blog that kind of walks you through this process. I will put a link in the description of this video if you prefer to read and want to follow through, but if you're more of a visual learner, an audio learner, and want to work with me, let's do this. So we've got 10 red organisms, 10 purple organisms, and 30 blue, and this is an incompletely dominant trait. We're going to use Hardy-Weinberg and chi-square to determine if the population is evolving or not. So step 1, set up an observed versus expected chart. Red, I'm going to put both the color, the phenotype, and the genotype just so I have it easily accessible. Purple and blue. I'm going to do observe versus expected. And we have the numbers that we observe. We observe 10 red, 10 purple, and 30 blue. There are a total of 50 organisms in this environment, but how many alleles do we have? If we have 50 organisms and each organism has 2 letters that make up their genotype, that means that in this population, oops, not 50 times 5, there are 50 times 2 per individual, 100 alleles in this entire population. We need this number a little bit later. That's number 2 here. So determine the number of alleles in that population. Now this is where a lot of people get stuck, is how do we figure out what the heck is expected here in order to solve this problem? So we need to, step 3, determine the expected frequencies for Q and P. So I'm going to start with Q. Now technically, because this is an incompletely dominant trait, you could start with P or Q. If that confuses you, just start with Q, like normal. You know, don't let that get at you. I can explain it. I'm not going to waste time doing it. So let's just jump in right with Q. Q, the frequency of Q. All right, frequency is always out of how many in a population, right? Q, if you remember, is the frequency of our recessive allele. P is the dominant allele, so we're out of 100 alleles in the population. Q, if that's recessive, there are 30 individuals who have BB, but we need to take this times 2 because these individuals can each donate that recessive allele, whereas here there's 10 of these recessive alleles coming from the heterozygote organism because they have 1B to donate, right? So just think 10 here, 30 of these, 30 of those. That's where that comes from. If you multiply all that out, we get 60, and this should be plus, sorry, not times. 60 plus 10 is 70 out of 100, and that's going to give us a frequency of 0.7 for Q. We know that P plus Q equals 1, so P is going to have to equal 0.3. Okay, we figured out our frequencies expected for Q and P. Now we need to determine the expected genotypes. So P and Q represent alleles. Remember that RR is P squared BB would be Q squared, and this is 2PQ. So now that we have P and Q, we can go ahead and take these to figure out our expected frequencies. We're not at genotypes yet, so don't fill this in just yet. First, let's start with, I'm just starting with Q squared. So the frequency is 0.7 for Q, which means Q squared must be 0.7 squared. And if you take 0.7 squared, let's grab the calculator, 0.7 squared, oops, I put in the wrong number, 0.49. Then let's do P squared is 0.3 squared, and that will be 0.09. And 2PQ, you're going to take 2 times 0.3 times 0.7, and I'm going to throw that in my calculator here, and I get 0.42. Okay, these are the expected genotype frequencies. We need to use this to figure out the expected number of individuals. There are so many steps to this problem. So if R P squared is 0.09, that's the frequency, 0.09 of 50, so I'm taking 0.09 times 50, is going to give us 4.5 individuals. My 2PQ, 0.42 times 50 individuals gives me 21 organisms. And my 0.49 times 50 individuals gives me 24.5. Double check that those add up to 50, right? That's one way to check yourself. That should make sense. We are not done with this problem yet. We are only through step 5. Step 6 is to chi-square this and see if the population is evolving or not. I do have room right here, so I'm going to go ahead and do this right here. We're going to take our observed minus expected squared divided by expected for each situation. I'm going to go ahead and calculate those. You do the same. Sorry that I'm a little sniffly. Okay, so I get 13.71 as my chi-square value. If you rounded differently internally, your number might be different, but it should at least be close. Now, degrees of freedom, this part can be a little tricky. When we determined our expected values, we were using our genotypes, right? P and Q, those alleles, which have two options. I know we have 3 different phenotypes here, but a genotype has 2 alleles. So the degrees of freedom is 2 minus 1, which gives us 1. If that confuses you, just know that your number here is 1, and yeah, just maybe you don't quite understand why, but just do it. So it's 1, we have 2 possible alleles minus 1 is what we use to eventually calculate our 3 possibilities here. Our p-value is always 0.05 unless you're told otherwise. If you go onto your chart on your AP equation sheet, that will tell you that the critical value is 3.84. 13.71 is greater than 3.84, so we reject the null hypothesis. The null hypothesis would essentially be that the population is not evolving, that we're in Hardy-Weinberg equilibrium, and we are tossing that out the door. We are saying, yes, the population is evolving because our chi-squared value is greater than our critical value. So that's how you solve Hardy-Weinberg chi-square combination problems.